Um, Today I'm going to be talking about Qiskit's architecture. Um, I can't see anyone, so feel free to interrupt me with questions as I'm going through. Um, and so when I talk about Qiskit in this presentation, I'm specifically talking about the Qiskit core SDK on GitHub. It's the Qiskit/Qiskit repository. Um, Qiskit is often gets confused because it's a whole ecosystem of projects and almost a brand. But what I'm talking about today is the architecture of the core library that is the base of all of that. And so that library is an Apache license to quantum quantum computing SDK that's written in Rust and provides public APIs for Python and a C API. It's collaboratively developed on GitHub with about 650 contributors. I just checked before, we still haven't hit 650. There's only 649 unique contributors to date. The project was originally started back in 2017 to provide a Python interface to IBM's quantum experience platform when IBM first put its 5-qubit quantum computer on the cloud. The original interface was just this drag and drop web UI where you would draw quantum circuits literally in a browser. And this was Qiskit started as originally just the Python interface to that platform. But it has since grown significantly. Qiskit provides a hardware agnostic interface to quantum computers and abstraction layers that let you reason about quantum information independent of the hardware you're intending to use. And as part of this, it includes a fairly mature quantum circuit compiler that lets you compile circuits as workloads that you can run on devices. Look through some examples of what I mean here. And so when we look at the design philosophy of this SDK, this is something I took from the paper we published a couple of years ago on Qiskit. And it falls into these categories being extensible, performant, portable across hardware, interoperable across abstraction levels, so you can work at varying different levels of abstraction for your programming, providing computational primitives for executing your quantum programs, and then also having visualizations to aid in debugging. I'm not going to sit here and read all of this because people can read faster than I can talk. But this is the guiding design philosophy behind a lot of the decisions we make at Qiskit. So as we go through this presentation, you'll see that everywhere we add an interface to Qiskit, we also add an abstraction model for the most part that lets you plug in and extend Qiskit's functionality to suit the needs of the application. And we try to do this in a way that's performant and also does not make assumptions about the underlying hardware. And so when we look at the architectural model of Qiskit, it's broken up into these modules of functionality in the library. So we have the quantum circuit, which is the main main structure in Qiskit that defines a quantum program, that defines a quantum circuit. And this is the primary entry point for users for defining their quantum program. We have a pass manager and transpiler, which is our quantum circuit compiler that I described earlier, and we'll go into that into some more depth. We have computational primitives for executing the circuits after they're compiled, and then dealing with results in post-processing. And this architecture diagram also shows the typical workflow where you have your initial problem statement, you build a quantum circuit, you compile it, you execute it, you post-process the results. And specifically for this presentation, I'm only going to be concentrating on this boxed area. So this is the core functionality of the Qiskit library. The other functionality either is used to build up that or is additional, but it's not really worth talking about when we talk about the core architecture of Qiskit. And so to look at that architecture diagram, but a little bit more concretely on a specific problem, this is just another diagram I took from the Qiskit paper because I think it very nicely outlines the levels of abstraction and a typical workflow where you have an abstract mathematical problem that you're describing. I don't remember exactly what this one is. It might be an Ising Hamiltonian, but it's a little hard for me to read the tiny font there. But you take that abstract mathematical problem definition, and then you convert it into the quantum domain, where you define it in terms of something a quantum computer can reason about. And then you take that abstract notion in Qiskit and synthesize it to a circuit. You run through the compilation routines to get what in the diagram calls an ISA circuit. We call it a hardware circuit in Qiskit's internal terminology, which is a circuit that maps to the constraints of the target, and then it generates whatever the output is for executing, and then you run that on your quantum computer. And so I'm going to go into the details of what is going on here, which is those core red boxes on the previous slide. But I'm going to start from the circuit, then I'm going to go to the bottom here and look at this piece here, and then we'll connect in the middle with the transpiler. So to look at Qiskit circuits, Qiskit's circuit provides numerous abstraction levels. It's the same structure in code, the same object that you work with, but it lets you create a very abstract circuit where you could have high-level operations that are defined solely by their mathematics or some abstract data type. And you can put that on a quantum circuit so that you can operate qubits on it and show the dependency of execution of the different operations. There's also standard gates and control flow representations, which are textbook quantum circuit gates that everyone who's studied quantum information theory is probably familiar with. Qiskit contains a library for that, and you can build your circuits at that level. You can also build circuits with parameterized gates, where you have unbound angle parameters that you can fit in at runtime or at compile time to let you reuse circuits between executions or compilations. And then also the thing I described before, which here is a circuit in terms of all hardware native gates and also with timing expressed. So in this circuit, there are delay operations that explicitly account for the timing. And then all of the operations in this case are in terms of operations on one of IBM's now retired quantum computers, which is this echo cross resonance gate and square root of x, RZ, and X gate, yes. And so you can build circuits at all of these abstraction levels. And to do that, Qiskit provides tooling that lets you do this with some basic building blocks. Like we provide a library for building circuits in Qiskit, and this defines a lot of different operation types at differing abstraction levels, as well as pre-built circuits. So this includes everything from like a library. I think right now the current count is 52 standard textbook gates that are like CNOT, Toffolies, Hadamards, measurement, obviously, and there's a whole list of them in Qiskit. And so if you're working with those, you can just build your circuit in terms of those. It'll be fairly performant because we bake those into. They're used pretty much everywhere, even in building hierarchical abstraction. So we want to make sure they're very fast to work with. And if there are standard gates that are missing, we can always add them to Qiskit, or you can define your own, which we'll look at in a second. And then it also provides abstract operations, like you could define a Clifford tableau and just insert that tableau directly in the circuit. And that operation is defined solely by the Clifford tableau and nothing else. Similarly, there's an operation type for a linear function, and you define the linear function in mathematical terms, and that you just put that in your circuit, and you can mix and match these abstraction levels as you see fit. Additionally, the library has some pre-built generator functions for building circuits of interest in research applications or benchmarking that provide like just performant builders that you can use as a starting point for benchmarking. So in this case, on the right here, I show an example of building a quantum volume circuit, which is just a common benchmarking circuit, and to build this very easily with that and interact with it, so you don't have to sit there coding out these common use case circuits. And as I alluded to, you can define custom operations. So Qiskit defines a core base class, or actually two of them, instruction or gate. The distinction here is instruction is not necessarily unitary, while a gate is a unitary operation and has certain requirements for when you define them. These two classes can be instantiated in Python directly, and you can just build a custom gate object, custom instruction. Or additionally, they're subclass safe, so you can define custom subclasses of them. An easy way to work with them if you just want to do a one-off for like to define hierarchical operations, to have a more compact circuit representation, either visualization or some other reason, you can take any quantum circuit and build an instruction or a gate from them with these methods. But then you can also define these custom subclasses. And this is the way that you typically define custom reusable operations in Qiskit that you can work with in addition to what Qiskit provides out of the box, because we can't, as a library or an SDK, we can't possibly know every conceivable operation out there. So we provide the tools to build your custom operations yourself and integrate it into the rest of the Qiskit workflow. So in this example here, I'm defining a custom square root of y gate. And it's very simple. And I just define what an equivalent circuit is for that gate, and also what its matrix, its unitary matrix representation is. And with this, then I can add the gate to my circuit just like any other gate. The one thing I want to call out here is because this gate is stateless and takes no parameters, it's more performant to define it as a singleton gate rather than a standard gate, because the singleton gate will mean that there's only ever one instance of it in memory, and it's always referred to by reference in Python, as opposed to instantiating a new object in memory every time you use it. This only applies, obviously, if it's stateless and doesn't take parameters, because if it had state, then it would obviously you couldn't reuse it. And so you can build. This is the equivalent of like what I defined as the standard gates on the earlier slide, where it's just like a standard textbook quantum operation. But you could also define abstract operations. So in this example, I'm defining, I called it a quantum string. It's not really a real use case, but it was just some fun abstract example I could think of that wasn't too complicated in mathematical terms. So in this case, I am building a quantum string gate that takes in an ASCII string and just encodes it in a circuit. So it looks at the ASCII binary representation and just sets an X gate if the bit is 1, and a 0 gate if the bit is, or an identity gate if the bit is 0. And this is just, it's not really useful for anything, but I thought it'd be fun to entangle the string high. So I built this custom gate, and you can see I just defined the definition here. And I instantiate it with the string high, and so now I have a string gate that encodes my quantum string. And then I build a circuit, and I put everything in state of superposition with Hadamard's, and then I just run my string gate. This is not a real example. There's no real use case, but I wanted to show that you can put anything in these gates, and they can also be fully opaque. So you don't have to put this definition here, and it'll be opaque in Qiskit. It's just a black box from the Qiskit standard data model perspective, but you can do custom operations on it when you encounter it, especially when we look at synthesis in the compiler. This is a common technique that people use where you define a gate that's opaque in the standard data model for Qiskit, but contains custom attributes that you can then use for custom synthesis during compilation. So if you have some mathematical operator that you want to encode in your circuit, and it's too involved to give a default definition, you just put the representation in the gate object, and then the compiler can reason about it with a plugin that you define to synthesize that custom operation into terms that the compiler can reason about for lowering to hardware. The last thing I wanted to talk about is the classical computation system in Qiskit. So in Qiskit, we define control flow operations for a quantum circuit. We call these dynamic circuits in Qiskit's parlance. And these control flow constructs are designed to be executed in real time. And in real time in this context means that it's classical operations that are designed to be executed within the coherence time of the circuit. So that these typically you have very limited time to evaluate these classical functions, especially on superconducting systems. And so the expressiveness and of the system is a bit more limited than like a true programming language that we're all used to, because it's not designed to run in a context where you typically have the same computational resources for classical computation that you do outside of the executing in the quantum circuit. And the other thing to call out here is that not all hardware supports these capabilities. Even in IBM's hardware, there's limits on what you can do with classical control flow in your circuit, and Qiskit can express far more than that. And so it really depends on the hardware you're targeting, on what you're able to do with this system. But just to show a feeling for how it works from Python, I've built this quantum circuit here where I have a for loop that's just iterating between from 0 to 9. And I'm just making a bell state, and then I'm measuring that into 2 classical bits. And then on each iteration, I just have this if test that's checking if the 2 bits are equal. And if they are, then I reset 1 bit, and I just build this random circuit break, and then measure the qubit that I was not using from before, and measure that out. It's just an example to show what you can do. I don't think this is a real use case. It's a little bit like repeat until success, but not quite. I was just playing around to show some of the capabilities. And so before I move on, that was all I really wanted to talk about with the circuit. I could go, on and on about Qiskit circuit data model more and more, but I wanted to keep it fairly brief and just show some of the core capabilities, because this is without going too much in depth in the weeds on that. So before I move on, are there any questions?
I have a quick one.
Sure.
Sorry, Spencer. Is it like all these descriptions that you mentioned, are they also available from the C API that you expose? Like building the different operations and the if, like the if, like for loops and if models and stuff, if conditions?
So not all of them yet. Specifically defining custom operations and control flow are not exposed to the C API yet. It's in plan for development in the next release, so the 2.5 release, which is targeting release in June. That should include custom gates and control flow, but we have not had an opportunity to expose them to the C API yet. The C API is still relatively new in Qiskit. We only introduced it about a year ago, and so we've been ramping up the capabilities in it as we go. But the other stuff should be like there's a circuit library. It doesn't have all of the circuit generators or the high level objects, but it has all of the standard gates and some of the circuit generators.
Sounds good. So we have Spencer and then Johannes. If you guys can make it a little bit quick so that we can move on with the presentation, though. Go ahead, Johannes, Spencer.
Sure. My main question is, so is the Python API, or is there like a Rust API, which is considered to be the main API?
So I have slides on this at the very end, but to give a quick answer leading up to that. So Qiskit is written in Rust with a Rust core, and it has 2 public APIs, a Python API, which is the higher level user interface that most people are using now because it's been around since the beginning. And then there's also a lower level C API. And we don't expose a direct Rust API because
I
Rust
see.
does not have a stable ABI, and so it makes reuse between different applications more complicated. So we just build a CFFI in Rust and
Right.
expose that as the public API.
Right. And so when you said that the C API doesn't have something, it's predominantly like you're focusing on the Python API and then you're adding things to the C API.
So I would say specifically on these capabilities here, they have existed in Python for years.
Mm-hmm.
We've only started exposing the C API in the past year. The C API was new in
Yes.
the 2.0 release that was not even a year ago. And so we're adding the capabilities to the C API to reach feature parity with what's in Python. All of these capabilities are in Rust at this point, but it's about building the interfaces to use that Rust data model that
Right.
we're still working on.
Right. Thank you very much.
Hey, I had one quick question about the classical control. If you could
Mhm.
go back one slide. Has there been thought put into like creating somewhat of a backend abstraction for the classical bits as well? Like if we start adding decoder boxes or things that, use this classical feedback, would it make sense to have like another backend class in the future?
So I'm about to talk about the backend
Oh.
class specifics.
Uh-huh.
So we can go through that there, but I'm not sure it necessarily requires a new backend class. There might be a way that we can augment the current target capabilities to better represent the constraints on control flow. But let's go through the backend section now, and then we can discuss afterwards if there are more questions on that.
Thank you.
So with that, let's go into Qiskit's backend model. So these are the definitions that we use, at least at IBM. I think we published a blog post about this, but also in Qiskit on the distinction between a quantum computer and a QPU. So we think of, in Qiskit, a QPU as all of the hardware responsible for executing quantum instructions, basically a quantum circuit and returning an answer. So this includes things like the control electronics around the chip. It's not just the chip. And then a quantum computer is the QPU plus the infrastructure to run tasks on it. And so in Qiskit, we have this model already where the QPUs is modeled with a target object, and the quantum computer, which is the QPU plus the infrastructure, is modeled with the backend and then also the primitives interface. And so these abstractions in Qiskit map to these definitions. And so when we look at this, you can think of as the QPU as part of a quantum computer, which it is. And then in Qiskit, the backend contains a target, which is a big part of it, which contains the hardware specifications of running a quantum circuit. And in the backend abstraction in Qiskit, we classify all of the attributes of a backend into one of three categories, where it's either required for the interface to be able to use it with Qiskit, something that's optional, but not required. This is something that Qiskit can reason about if it's there, but it's not required to work with. It might improve performance or let Qiskit reason about your backend in more with more fine-grained detail, but it's not required and can work without it. And then the capability for something that's custom, because with any abstraction, it's never going to be perfect. And so we wanted this abstraction to be able to facilitate people putting things in that Qiskit can't reason about, but be able to still leverage Qiskit's infrastructure to work with it. And so we'll look at some examples specifically with IBM's implementation on how these custom attributes can be used. But I know of several other backend implementations that are leveraging this mechanism. And so when we look at the backend class itself, there's a backend v2 abstract class, which defines this interface in Python. And what is required is the backend has to provide a target, which provides that definition of the QPU's constraints, and then also a run method for executing a quantum circuit. And then there's another bucket of things that are either optional or custom. And just to look at implementations out there, I collected this table of some to quickly show some of the distinctions here between different implementations of this abstract interface. So in Qiskit, we actually only have one. We call it generic backend v2, and it's strictly for testing. It's a customizable class that you instantiate. It just has some like syntactic sugar for quickly building a fake backend for testing purposes. And its run method is implemented with one of two simulator backends, depending on whether you have Qiskit Air or not installed. And it's strictly for testing in Qiskit. And then the Qiskit library itself does not contain any details about any specific hardware implementation. This model is designed so that you provide a implementation of this as a separate package that can then be used for interfacing Qiskit with specific hardware or simulator. And so then I picked two examples of hardware vendors providing packages and two simulator examples. So the blue are the simulators and the red are the hardware. And I'll concentrate on the hardware for this slide. So the two I put here are IBM backend is an implementation of backend v2 and the Qiskit IBM runtime package. And these backends are built from API responses from IBM Quantum's service. So this backend queries a REST API, receives some metadata about individual quantum computers that are on IBM's platform, and then builds a backend object. And then the AQT resource is an implementation of backend v2 for Alpine Quantum Technology, which is a trapped ion company out of Austria. They build their target. Actually, it's hard-coded in their provider. They don't query an API to get any details. Their hardware is fairly homogeneous, and they don't provide a lot of details about error rates or any of the other optional information. So they just encode a fixed target in software to represent different classes of system, and then when they run, they submit to their systems. And just out of curiosity, I did some time last week searching for all of the provider implementations that I could find. And I don't claim this was an exhaustive list, but I went through all of the examples I could find on GitHub and PyPI that were using any of these interface abstractions in Qiskit and providing concrete implementations of them. And I found a fair number, actually, a lot more than I expected, including several, actually most of the hardware vendors that I'm aware of provide implementations of this abstraction so that you can leverage Qiskit to run on a particular vendor's quantum computer, but then also a fair number of simulators as well. Yeah, it's just a big list. I'm not going to try to read through it, and I'll share these slides afterwards, and you can look through them at your leisure. I don't claim to know anything about the state of any of these projects except that they exist. I wanted to talk a little bit to show an example of like what this custom functionality that I keep referring to is. So in the IBM backend that I showed on the earlier slide, that's the implementation for IBM's implementation of this interface. They provide a lot of extra details that are not part of the interface that's defined in Qiskit. And there are all of these attributes or methods that I listed here. Qiskit doesn't have a reason, it doesn't have this in its core data model, but this backend object provides these custom extensions. And what this means is that if you want to work with them in the provider or in some package that's built on top of it, you have to understand that this is only an IBM thing and it's not a Qiskit thing. And so when you work with this, you have to come at it with this understanding. I also wanted to talk about the primitives, which I mentioned on the earlier slide. And the primitives provide a different interface for running, and it operates at a different abstraction level. So the backend models the quantum computer, but it's very free-form by design. We didn't want to, when we defined the backend v2 interface, we didn't want to force a particular implementation of it to dictate how it returned results from the execution of a quantum circuit. So we defined this results class that was purposely freeform. So you could return any result data that represented the way computation worked on your quantum computer. There was a bias in that class for what we called counts returns, which is, you can think of it like a histogram. It's just literally what was the sample from running one shot of that quantum circuit, and how many times did you encounter that. And so if you return data in this format, they're provided tools and an ecosystem for using it, but it was not a requirement. And so a perfect example of this is some simulators that are using like a state vector simulator, for example, might just return the state vector. Or if it's a stabilizer simulator, it might return the representation of that for simulation and not, not counts. It might not sample the quantum circuit. It might just, return its internal state representation. So you can think of this run interface in the back end as you give it a quantum circuit and it will return something. When people started building applications on top of these backends, this led to issues because you didn't know what the output format was going to be necessarily. You'd have to check it whenever you were giving something that implemented this backend interface. You would get some result and you would have to inspect it to figure out how to work with the data. And so that's when we added this primitives abstraction, which is supposed to model the computation on a universal quantum computer. And it provides two abstract interfaces for sampler and estimator. Sampler is sampling. So you give it a quantum circuit and it returns the raw samples from execution of each shot of that quantum circuit on the hardware. And then the estimator is for expectation value problems. So you give it a quantum circuit and an observable, and it will return the expectation value of that observable on the circuit. And these define very concrete input and output formats so that when you're writing applications, you can know what you're going to get in the output. I'm not going to go into as much detail on what these interfaces look like, but you can think of them as a more constrained execution interface than the run method on the backend object. And if you are implementing a backend v2 that returns counts, then Qiskit provides a default implementation for these sampler and estimator. But the real power of them can be if you provide a bespoke implementation for particular hardware, you can take advantage of some of your particular runtime environment to give a better or more performant implementation. But there's still a default that you can use in Qiskit if you had already implemented a backend v2 and used counts. If you used something else, then obviously this can't reason about it because Qiskit has the same problem that applications developers had. And so I've talked a lot about the target. And so I wanted to look at what that is because it's a big part of the backend interface. It's one of two required things. We already just talked about the run side of the abstract interface. The other required one is the target. And the target gives the compilation constraints of the QPU to Qiskit. It's how we model what the hardware is capable of doing, and tells Qiskit when it's compiling for a particular QPU how to reason about what it needs to do to be able to run on that QPU. At a high level, you can think of it as containing a list of every instruction, which is its operation or gate on individual qubits, and the properties associated with that instruction. Typically, out of the box, it's error rate and duration and maybe bounds on parameter values. But this is very freeform, so you can define targets that allow heterogeneous gate sets. So you have gates that operate on different subsets of qubits. So you could define, CX on 0, 1, CZ on 1, 0, or something like that. And then there are also additional properties around qubits and other device characteristics like scheduling constraints that are contained within the target. The one place where I want to call out that this is a little bit weaker is on the control flow. So the way we define control flow in a target is in the abstract this QPU supports running an if-else operation, or this QPU supports running for loop. And that's the extent of the expressiveness for control flow on the target. And this is something that we probably will be looking to extend in the future if people have ideas, because that often can't capture the nuance of what the limitations of these classical operations are inside like a real-time execution environment. And so just like the backend abstraction, the target classifies data into 3 categories, where there's required, optional, and custom. Required and optional, Qiskit provides compilation tools that can work with that, but custom, by definition, Qiskit can't. But the transpiler in particular is designed to be able to enable extension, and it's pluggable and modular. It makes it very easy to work with custom data in the compilation for vendor-specific or hardware-specific constraints that you have to worry about in compilation. And this is often used because the target model can't capture the semantics of the constraints of any conceivable hardware. And so we put this specifically in the data model to be able to extend the compiler to when it's especially working with as it's lowering towards hardware, to be able to work with the unique constraints that the abstract data model can't fully capture. And so when we look at what's in the target, we can look at what this data is. And so what's required in a target is you have to specify how many qubits this target has, and then what the supported instructions are, which is just the gate object or the instruction object. It's literally the object that we looked at in earlier slides from the circuit model, and then the qubits that instruction operates on. And then optionally, you can define qubit properties, which are physical properties about the qubits, and then instruction properties, which are things like error rates or durations that are associated with each individual instruction in the target. And then there's also global timing and alignment info. And then anything outside of this is treated as custom. And so if we look at that target description I showed earlier, you can see that it breaks down quite cleanly in how the string representation of a target is printed, where the required stuff ends up being on the left and the optional ends up being on the right. And to show how this can be customized is we can look at IBM's implementation of the target in the Qiskit IBM runtime package, where Qiskit defines the base qubit properties, which only contains T1 and T2, the coherence times, and then also an operating frequency for the qubit if you wanted to do some analysis for compilation based on that. And then you could subclass qubit properties, and so Qiskit IBM runtime does the subclass safe class. And so there's this IBM qubit properties class, which contains the core data model components, and then extends it with custom attributes for IBM's particular implementation, with extra metadata about each individual qubit on the processor. And so to show what this looks like in practice, I wanted to show just a very high-level overview of running an application circuit, or in this case, a benchmarking circuit, on hardware, and show what that looks like between IBM and AQT, which is why I put those two on the slide. So in this example with IBM, I'm building a quantum volume circuit and just adding measurements to it. And that's what this diagram that I bet no one can make out all of the individual unitaries in there, because I can't. And then we import the Qiskit IBM runtime package, instantiate it, and uses my credentials, which are stored locally. I pick a particular backend. I then compile the circuit with the transpiler, and I get this output, which is the ISA circuit, that hardware circuit that's executable on the device. And then I use the package and its sampler implementation to submit this for execution. And when we look at this, the analogous component from the classical compiler world is the machine code generation. All of these systems tend to be very limited resources and behind REST APIs or some other API abstraction. So for submission to IBM system, there's a JSON-based payload that goes over a REST API, and the circuit is encoded using a binary serialization format in Qiskit called QPy. And then that's, I almost said UU encoded. It's base64 encoded and just embedded in that JSON, and then sent over the wire for execution. And then you get your results back. And, yeah. And so then to look at what the workflow is in AQT, it's very similar, but also with some key differences. So building the same quantum volume circuit, instantiating the provider package to get a handle on submitting to AQT system and the hardware definition. I'm picking a backend. And the thing I mentioned earlier, but unlike the IBM system where it queries the REST API to get the metadata about the processor, AQT doesn't provide that level of detail. And so inside their code, their target definition, it's not exactly this. I simplified it for brevity, but it basically looks like this, where it defines just the target, the number of qubits, and these instructions are global, have no error rates, have no durations. But this is how the processor operates. And then when we compile the circuit, we get this very different looking implementation for execution on the hardware. And then when we run it, they don't have the same sampler interface implementation. They have an earlier version of it, but I just used backend.run and submitted the circuit, and it sends the machine code, in air quotes, representation of that circuit as a very flat JSON object where it's literally a JSON list. And it lists out the operations as JSON objects in that list. So each individual operation, its parameters and qubits. And that's what it sends over the wire for execution. And then you get your results back. And so I wanted to show this to demonstrate like this abstraction lets you capture actually all of the details about execution on universal quantum computers and provides a framework for building circuits independent of hardware. But then when it comes time to execute on hardware, it provides the tools for Qiskit's compiler to reason about compiling whatever level of abstraction in your circuit and your program is down to hardware. And then I wanted to say plugin, but it's not quite plugin system, but this provider package and abstract interface implementation lets you run on any one system. And so I could look at any of those packages on that giant list and run the same circuit in the same way. And who knows what this output is here. It depends on each individual implementation to execute. Some of them might not even go over the wire. A lot of the simulators don't, in particular. For example, Qiskit Air does this all in memory. It takes that quantum circuit object in memory and just does its state manipulation without ever serializing the circuit, for example. So with that, I wanted to then transition into talking about compilation. I quickly check if there are any questions. No, it doesn't look like it. Then I will move on. So in Qiskit's compiler, the intermediate representation that Qiskit uses by default is this DAG circuit representation, which is a data flow graph representation of all of the operations in a quantum circuit. It tracks the flow of data from qubits at the start of the circuit to qubits at the end of the circuit. And each operation ends up being a node. And the edges just track which bits or classical variables are being fed into each subsequent operation. And this data flow graph view makes it very useful and performant for doing a lot of the compiler optimizations or analysis that we need to do as we operate on them in compiler passes. In particular, it simplifies in-place mutation and substitution because we can reason about the data dependency around each individual operation very cleanly. And I want to call out that this is the default intermediate representation that Qiskit uses, but it's not the only one. And in particular, the infrastructure for Qiskit's compiler is IR agnostic. So you could use the infrastructure in Qiskit for building a compilation pipeline and never use the DAG circuit. All of the defaults built into Qiskit do use the DAG circuit for the most part, but it's not a requirement of the infrastructure. And we left this level of modularity because looking to the future, the DAG circuit is probably not going to be the only IR that we want, especially when we start looking towards fault tolerance. There are going to be different levels of abstraction, and we'll probably want to add different intermediate representations for different programming representations as we go through the compilation workflow. And so when we look at the compiler architecture, I'm going to interchange compiler and transpiler. It's like its proper name is the transpiler, but it's a compiler. So if you hear me switch between them, I'm just saying, I'm referring to the same thing. So the Qiskit's compiler architecture is defined around compiler passes, which are, you can think of, I like to think of them in like the Unix software philosophy of do one thing and do it well. So you have a pass that does a concrete, small, well-defined task, and you run a series of these on a circuit to transform it from whatever the user input representation is through to something that can be executed on hardware and is performant on that hardware. And Qiskit has a large library of passes that's built into it, but it also defines abstract interfaces for writing custom passes, and then also interfaces for hooking those passes into Qiskit's built-in pipelines or defining your own pipelines with your own custom passes. And those pipelines are built into this pass manager abstraction, which is the structure that deals with the complexity around scheduling and execution of passes. And it supports control flow in this structure. So you can build a pass manager that has do while loops, if statements, for loops, that kind of thing. And in Qiskit, we build preset pass managers that are already configured for different optimization levels between 0 and 3, 0 being no optimization, 3 being we throw the kitchen sink at it. And that you can build these preset pass managers and manipulate them and change them as you want to. And the other thing that the pass manager does is have this global property set for passing metadata between passes. So you can put some metadata in that property set and then have a subsequent pass act on that metadata. And to show what this looks like in practice, I just built this quick pass manager. It's not a real example. It doesn't really do anything except demonstrate some of the capabilities. So I build this pass manager. It takes in a target because you have to instantiate the passes with what they're targeting for that instance of it. And so I just build it. I put a couple of simple optimization passes on there. Then I defined a conditional control flow. So this is like an if statement. So if this choose layout condition returns true, then it runs this trivial layout pass. And this can be a list of passes or can be its own pass manager. And it will nest it inside this conditional. Then I run some more passes that take the output of that trivial layout, which puts a layout on the property set. Then it will run these passes to transform the circuit based on that layout that's found. And then I run an optimization loop. So I have this do while loop that runs all of these optimization passes in a loop until it reaches a fixed point, which is checked by depth size fixed point. So we run a size and depth pass on each iteration of the loop. And if two iterations of the loop have a fixed point and depth and size of the output circuit, we break out of the loop, and that's the end of the pass manager. And so when we look at what the data flow graph, control flow graph is of this pipeline, you can see it visualized here on the right, where we have a conditional control flow here and then a do while there. And so this lets you build pass managers that can be pretty expressive programs that run these passes in various different ways, and it's very freeform. But then oftentimes compiler pipelines are more than just like freeform execution graphs like this. And there's often typically a standard flow that you want to run in each with concrete steps. And so in Qiskit, we have the layer above the pass manager to represent this. We call it the stage pass manager, where you break a compilation workflow up into discrete stages, and each one of those stages is a pass manager like I previously described. And these stages execute linearly. So you could have, in this example here, I showed the 6 stages that Qiskit's preset pass managers all use. And these execute linearly. So you run the init stage, then it's immediately followed by the layout stage, which is followed by the routing stage, and so on and so forth. But each one of these stages could have like a giant loop in it, or a very deeply nested if-else structure. The preset pass managers in Qiskit are designed specifically to take a very abstract circuit in, do as much optimization up front, then start the process of lowering it to hardware. And once it gets something that's executed by hardware, then run optimization again. And in particular, this optimization stage here is just basically a giant do-while loop. And it runs a lot of passes in it. And at each increasing level of optimization, well, between 1 and 3, what gets run in that loop increases. And so then there's a trade-off between execution time and potential optimization. It obviously can't guarantee optimization because you should run more and it might not improve anything. And so while Qiskit defines these 6 stages, if you're building your own staged pass manager, you can define whatever stages you want. And a good example of that is actually in this upcoming Qiskit release 2.4, which is targeting, I think, April 2nd is the tentative release date for the 2.4 release. We're adding a second staged pass manager for Clifford plus T targets. So if you provide Qiskit with the target and it's in a discrete basis set of all Clifford gates and T gates, we built a different stage structure. I think it has 8 stages because the compilation workflow for doing from an arbitrary abstract circuit to a Clifford plus T target is a little bit different. So the stage structure there is different. And I don't remember what the 8 stages are off the top of my head, but they are different. And so with this modularity, then comes pluggability or extensibility. So once we have these defined stages, then if you're working with compilation, oftentimes you don't want to replace the whole workflow, but just pieces of it. And the defined stages makes it very easy to plug in replacement implementations. Well, if it's a free-form, execution graph, it's obviously harder to place something in the middle if you don't know what the structure of it is ahead of time. And so these stage pass managers, we define them to be extensible. So you could just modify it in place. So you could generate a preset pass manager. You have your 6 stages, and you say, I'm not so fond of Qiskit's layout algorithm. I'm going to replace it with a different mechanism with my own stage implementation. And you can just substitute it in place. Qiskit will run the transpilation in the same exact way, but then run your custom mechanism. But then also we provide a plugin interface for Python that lets people package plugins for each of those stages. And then when you generate the pass manager, you can just specify the plugin by name instead of having to manipulate it in code. And so in this example on the right, there's this Qiskit qubit reuse package that implemented a particular optimization technique from a Quantinium paper to use mid-circuit measurements to reduce the width of a circuit, so decrease the number of qubits. It does some analysis of the causal relationship between of operations in the circuit to figure out where there's a clean splitting point where you could reduce the width and just reuse qubits if you do a mid-circuit measurement followed by a reset. And so this technique actually works very well on a Bernstein-Vazirani circuit. So that's what this circuit shows here. And then if I run generate a preset pass manager and I say I want to run with this init method, and then I run that pass manager, you can see it does the qubit reuse, and it reduces this 4-qubit circuit down to 2. And so you either use the function to just one-shot execute the transpiler, or generate a preset pass manager, which gives you the object, and then run it. And this just pulled it from this package that's on PyPI. And so this can be, people can publish this on PyPI or wherever, but provide reusable implementations of each of the stages in Qiskit's preset pass manager to just plug into it and provide an alternative for one common use case is custom transpiler passes for backends, which I'll show in a second, but also this is an active field of research. People often come up with new novel implementations, and they can package it like this to get people to experiment with it. And so how does this connect with the backend v2 interface? So the backend v2 interface defines optional functionality to provide a plugin to use for different stages in the compilation. In particular, there are hook points in the backend interface for setting the translation stage or scheduling stage, which will be run by default. So you could, as a backend implementer, you could say, package your own translation stage, expose it as a plugin on your package, and then use this method that you put on your backend class implementation and say, when you're compiling from my backend, don't run Qiskit's default stage, run my stage instead, because I have some constraint that Qiskit doesn't know about. It's custom for this backend implementation. So run my compilation stage instead. And the transpiler will just pull that stage in and run it, just like if the user had specified the plugin. And this gives a really powerful way for being able to leverage that custom aspect of this data model for compilation in particular. And so to show what this looks like in IBM's backend in particular, it leverages this. So there are some constraints about dynamic circuits that I mentioned. Target has very limited semantics around control flow, in expressing the constraints around control flow. And so IBM Quantum's implementation, you can read the documentation. There are a lot of limits around control flow operations and inside the coherence time of a circuit. And so there's a custom stage that knows about those constraints. And similarly, there's this IBM fractional thing, which I don't think is there anymore. It was a pass to handle rotation, like rotation bounds on 2-qubit gates that take a parameter. But that's no longer necessary, so I don't think it's there anymore. The other thing I wanted to talk about on the transpiler extensibility is that while we have all of these plugin interfaces, that's not the only way that you can extend the transpiler. There are a lot of the data structures that the presets in Qiskit are built with are also extensible to handle custom workflows. So a concrete example of this is if you have hardware that takes custom operations that are not in Qiskit's circuit library, I would encourage you to reach out and open an issue to add it to the circuit library if it's something that's common. But if not, you can leverage the mechanisms and the extension points at every level of the transpiler to leverage. So in this example here, I'm just taking our SY gate that we defined in an earlier slide, and I want the transpiler to be able to reason about it. So in that 6-stage pipeline, there's a specific pass, the basis translator, which is used for translating all of the gates in the circuit once it's lowered to a point where they're all discrete operations that hardware can know about, like all textbook gates are lower. That pass has a giant library of equivalence relationships between different operations. So it says, like, a Hadamard gate is implemented like this way with these gates, and it traverses that library. It's actually a giant graph, and figures that and does recursive substitution until it finds a path through the graph from what your target supports to what's in the circuit, and then it does that substitution throughout the circuit. And so you can just extend that library of equivalence relationships with your custom gate definition. So you tell that library, okay, here are some standard gates that Qiskit knows about. Here's how you translate from that to what this gate is. And so here for the square root of y gate, I just showed going from a Hadamard to z plus sy, and then also u2 from u2 to z and sy. And then with this information in the library, that this transpiler pass has enough information to figure out how to do this translation. The obvious caveat here is this is only one pass, and so it won't understand how to do optimizations with this gate because nothing else in Qiskit's pass library will understand how to work with this gate since it's fully custom, and that's where we have those other mechanisms in place. Or come to Qiskit and open an issue or open a PR to extend the library to support your extra operations so that we can reason about them in the preset passes.
Hey, Matthew, we're
Yes.
at the top of the hour. I just want to make sure that people are going. I don't mind going on, but just so that people know that we're going to continue with the presentation.
Okay.
If people are fine staying, that's good.
Okay, yeah, I should have plenty of time, so I can keep going if people don't mind.
That's good.
Okay. So the other plugin point in the transpiler that I wanted to highlight are synthesis plugins. And so this also connects with custom gates that I mentioned before, especially the abstract one. So Qiskit's compiler provides 2 plugin interfaces for synthesizing abstract or higher level operations. There's a unitary synthesis plugin and a high level synthesis plugin. Unitary synthesis plugins are designed to take a single object called a unitary gate, which is just it's a gate that represents an arbitrary unitary matrix that represents some operation. And this plugin interface just takes the matrix from that unitary gate, gives it to the plugin, and the plugin returns a circuit, and that implements that unitary. And the synthesis is used by a single pass in particular, unitary synthesis pass, and Qiskit provides a default plugin, but this is extensible to do any kind of synthesis that you need for unitaries. And the compiler in particular does a lot of unitary synthesis because a lot of optimizations involve taking a sub-circuit, computing its unitary, and then doing people optimization on it. So like if you have a better synthesis method or a synthesis method that's better for your hardware, your hardware's gate set, you can leverage this plugin interface to leverage that. The other plugin interface is a bit more powerful and a bit more open-ended. So we call it the high-level synthesis plugin. And it's designed to take any operation as an input and then return a circuit that implements that operation. And so Qiskit itself defines, I lost count, it's at least 50 plugins for this that represent like abstract operations and different synthesis methods for that operation. A very good example of this is Clifford synthesis. So I showed on an earlier slide that you could put just an arbitrary Clifford tableau in the circuit, and then the compiler would reason about it. Well, we have numerous high-level synthesis plugins in Qiskit to synthesize Cliffords into discrete gates. But additionally, there are external packages to do this because this is a field of active research. People come up with different techniques for it. And these plugins are used also by a single transpiler pass high-level synthesis. And so on this example on the right, I've just built this circuit with 2 high-level objects. One is a random unitary. It's just a random unitary matrix on 4 qubits. And then I built a random Clifford and on 4 qubits, and I stick that in the circuit. Then I installed this Qiskit SAT synthesis package that's on PyPI, which has uses an SAT solver. I think it's Z3, if I remember correctly, to model the Clifford synthesis problem as a SAT problem, and then figures out the synthesis is there. And so I can define this configuration for high-level synthesis, give it to the pass, and this argument can also be set on the pass manager level as well as the standalone one-shot transpile function. And I give it this configuration that says use this SAT optimizing for depth method from this external plugin, set a couple of flags that are special for it. And then also for unitary synthesis, I just picked a plugin from Qiskit's built-in library of plugins that does approximate synthesis. I'm not actually aware of any external packages that implement that interface. That doesn't mean there aren't any out there, but I'm not aware of any off the top of my head. But then if I run the high-level synthesis pass and I display the circuit, you can see it synthesizes that Clifford into discrete gates using that external plugin. And then if I run the unitary synthesis pass with this approximate quantum compiler plugin, which does an approximate synthesis, so it's not fully implementing that unitary. There's some error that's introduced by the synthesis to save gates. I don't remember what its default tolerance is, but it synthesizes that into a much deeper circuit, and the Clifford is still there in that tiny little box. But this also gives you a level of like pluggability and extensibility in Qiskit's compiler infrastructure that lets you hook in at a very fine-grained point if you need that level of optimization, or that you need that level of flexibility, but don't want to re-implement everything that Qiskit does for some custom workflow. So the last thing I wanted to talk about is the C API, but I guess I'll pause here for questions in case anyone has any again. Doesn't look like there are any.
Yeah, since we're over time, let's keep going with the presentation because it'll be good to get it all through, and then we'll have open questions afterwards.
Yeah. So I'll try to go through this quickly, and I didn't go super in depth in detail. We talked about this a bit already, but Qiskit itself is primarily a Rust library at this point. I mean, if you look at lines of code, it's just shy of 50% Rust at this point, and all of the core data model for everything that I showed on these slides is all operating in the Rust domain, even though I was demonstrating it through Python interfaces, with the exceptions of the things that we already talked about. And so the way Qiskit is architected underneath is that we have a library of Rust crates internally, which don't expose a public Rust interface. We just use them internally to build these two interface definitions. One is for Python, and that compiles out to this accelerate abi3.so shared object file, which defines a Python C API for an extension, which then Python interprets as this private module inside Qiskit's Python code. And then Python code can use Qiskit, and it calls this internal accelerate module, which is all Rust code underneath. And then if you're using the C API, you can build standalone C interface, which compiles out to this libqiskit.so, and we generate a header that defines the interface to all the symbols in that shared object file. You can build your C program that uses libqiskit.so. And there's also a mode where you can combine them. So we also expose the C API from this accelerate abi3.so, so that you can write Python extensions that leverage Qiskit C API to accelerate that. So if you wanted to, if anyone has done this with NumPy, for example, NumPy has the same basic model where NumPy is exposed to Python, but also exposes a C API so that people can write extensions around NumPy that improve performance. But I'm not going to talk too much about that. And so what the C API lets you do is have very low-level access and write compiled language programs, which are going to be a lot faster than Python. But it also forms like a very core layer that people can extend with any programming environment or language that they like. Because I'll be honest, I did professional C programming for many years, and I don't miss it. And so C is not my choice, but everything can talk to C because most operating systems are written in C, and you have to be able to talk to a C API to allocate memory, or simple things like that. And so Qiskit provides these two interfaces. So I showed building the same circuit here between Python and C. It's just a simple bell state. C is a little bit more verbose, but they do the same thing. But people have already started layering on top of the C API. And so one concrete example is C++. There's language bindings that it's a header-only library that just calls the Qiskit C API under the covers, but it uses, ergonomic C++ programming, and, modern features like namespacing. Then there's also Rust bindings that's been developed by the community around the C API. And then also Julia, because there's a very dedicated Julia user group in quantum computing. They're very interested in leveraging this for programming quantum computers from Julia. And my point here is, though, that while these are 3 concrete examples today, the goal of the C API was not to just enable C programming, but it was to enable anyone to leverage Qiskit, to enable letting any programming environment leverage quantum computers. And having a C API is a very natural choice for that. Even though there were specific technical reasons with we were doing everything in Rust, and the C API was very natural for this kind of reusable interface, having a C API is also very natural to let anyone interface with Qiskit, and then by extension, any quantum computer. I mean, you saw that huge list of all of the hardware implementations or provider implementations that use Qiskit to interface to hardware or simulator. If we can extend this ecosystem to any programming environment, that really democratizes access to quantum computing. And I'm going to skip over this. It's just one of the demonstrations we did to show that the C API was complete. Is we demonstrated this hybrid HPC quantum workflow using the C++ bindings on top of the C API to demonstrate an SQD algorithm from this paper that was published a year ago, and just executed it as a single MPI-aware C++ application that you could run. That we ran it on Fugaku and then also some internal clusters. And we ran this application, and it would call out to the quantum computer, get samples, and run the algorithm as a mix between MPI C++ code and Qiskit to demonstrate how to do this all as one normal HPC workflow. And so with that, I think that's my last slide. And I have some time if people still have questions, but we can also end here since we're a bit over time. And I threw up some links here to the GitHub, the product page on IBM's website, and then some documentation. And that QR code goes to our paper, our preprint on archive, if people are interested in reading that paper. And so with that, that's the end of my slides. Thank you.
I think it's a good opportunity to open it up for questions if people are interested. I have some, but I guess I'll leave it to the floor. If anybody has questions, they can raise their hands, and then we can go on from there. All right, I'll start first. If we go to the very first slide where you showed all the different components,
this one,
the different, yeah. So when we talk about the different components, are you guys thinking about exposing the blocks independently so that you can have them standalone sort of thing, so the transpiler can work with different program, outside of Qiskit, quote unquote, kind of thing?
So trying to think so the transpiler here, the way it's architected, it's very specific to, so for the preset path managers, it's very specific to Qiskit's data types, the quantum circuit, the DAG circuit. All of those presets are built assuming that right now. The infrastructure for itself is not. We haven't really thought about exposing it as you assume you're asking in the sense of would you expose this as a standalone transpiler library that anyone could use independently of the rest of Qiskit, or? Yeah,
that's the question. And because when you were describing the path manager, you had all these different plugin architecture and infrastructure to allow for customizing different pieces of it. And it seems like the infrastructure itself can be it doesn't have to be tied with a specific circuit representation, I guess. If that makes sense.
Yeah. So I mean, I guess that comes down to a packaging question. From a design philosophy point of view, we definitely are thinking along the terms of like modularity and not part of it is, besides like, extensibility and future use cases, it's also just about not tying our hands, because this is still like a very actively growing domain. And so we don't know what the future holds. Like in discussions on fault tolerant compilation in particular, we're thinking about a lot of different ways of representing it. I don't think we've ever thought about breaking it out into a standalone library. We try to keep Qiskit fairly lightweight on its own. And so even if you're only using this one submodule, I'm not sure if there's benefits to breaking it out even more fine-grained into individual packages. Does that answer your question, or we can talk more about it if it doesn't?
Yeah, and the other thing I was thinking, so like in the C, when we talk about the C API, I looked at it briefly. I haven't delved into a lot of details, but it does expose, for example, your quantum circuit. It does expose how to add gates, customize the gates, etc. And I've seen, I think, some APIs that do transpilation specific things, like adding a transpilation pass or like customizing the transpiler in some way or configuring the transpiler somehow.
Yeah. So in the C API, like we have quantum circuit, and so you can build a circuit. There are some limitations versus Python on what you can do in C at this point. But then we also expose the transpiler both as a one-shot, so like as a standalone function that says, here's my target, give me a circuit and I'll compile it for that target. Or the preset stages are defined as functions in the C API, as well as individual passes, so that you can like mix and match. But we don't have the pass manager infrastructure in C that I described from like Python. That like execution graph doesn't exist. The thinking was we concentrated on the quantum specific bits first, because we thought that's where the most power was in the short term. Because you can always write a C function that mirrors that. It's very easy to write like an execution graph in C. It's just code. So we thought that would be a more natural starting point, and then we're looking at doing that whole like staged pass manager system that I described in C, maybe the second half of this year, because it's based on like what people have time to work on, and we've been prioritizing like getting the basic workflows running in C, and then going from there.
Does anybody else have questions? All right. So you mentioned also target and backend, and do those have C APIs? Do you export them through C right now, or is the main target like the main?
So
I guess
the target is exposed through C. The backend is not exposed through C yet. The reason is, you might have noticed I was talking about the differing abstractions between backend and primitives. We're planning to do a new version of the backend interface for the next release, 2.5, and that will be Rust native to start. And that will expose that to both C and Python at the same time. The way the backend v2 was written, I did it, God, at least 5 years ago. Like Rust wasn't even on the table in Qiskit back then. It was still very early. And so like all of that is written assuming Python. And so like we're thinking in the next release, we're going to do this in Rust to start and then expose it to both C and Python at the same time. And also like try to combine some of those like differing abstractions to make it a little bit cleaner.
The other thing is right now, do you guys support any multi-backend support? So say, for example, in the future, you have, like 10 IBM machines that look exactly the same. Will the person that's writing the application, will they have to account for all the different backends? Or are they going to be able to have some sort of an abstraction layer that sort of, manages the distribution of the different circuits that you're trying to execute to the different backends?
So I think for current hardware in particular, you definitely, they're not homogeneous. The backends are not fungible. You can't compile for one backend and have it expect to work the same on a different one, even if they're the same underlying architecture. So for example, on IBM systems, Heron and Nighthawk are the current generations of QPU architecture that we offer. If you compile for one Heron, even if it's the same generation, that circuit will not necessarily execute well on a different one. So for a current state of hardware, you want to compile for each individual backend that you're running for. The what I showed here on this slide is that from like an application point of view, it doesn't really change anything from your workflow, where you build your program, you build your circuit, and then you give it the backend that you're compiling for. So if you had some scheduling system that is provides your backend to you and gives that to you as the Qiskit object, from the application level, you just say, okay, I've got this backend, compile for it and run. And that's the way we built the abstraction Qiskit. Now, whether those 10 backends are represented by the same object and it's just a different endpoint for dispatch or not, that's an implementation detail of who implements that backend. But like from the abstraction point of view in Qiskit, like it's all abstracted away with this backend interface from the application programming side.
True, but what I'm thinking is right now it seems that the backend assumes a single hardware, single simulator on the backend. But let's say, for example, in an HPC environment where you have a bunch of resources, you have like a bunch of quantum computers, and a job gets access to 2 or 3 quantum computers, right? Now, the application, in order to make use of the 3 quantum computers, how would it reason about that? Or would it say, okay, well, I'm going to create 3 different backends and I'm going to manage the use of those backends independently? Or is there some thought about, well, let's create some abstraction layer that abstracts away the 3 backends and let the application have a mesh that it deals with, for example, and then it says execute on there, and then there's some other layer that decides where to execute based on whatever criteria. Say, for example, you have, I don't know, like the best available one or the best least noisy one or something like that.
Oh, yeah. So I'd say that you could do it 2 ways in this model. So you could define a backend implementation that handles the dispatch to that mesh under the covers. And so the user doesn't necessarily need to know. The complexity there is in the implementation, because you do need to compile the circuit at some point, because you don't know at what level of abstraction the circuit is written. So you do need to compile it. And this backend interface tells the compiler all of the constraints of the backend. And at least on current hardware, like there's a one-to-one mapping. You could build an abstract target, but you would not get good compilation that would result in any signal out from the execution. And so you would have to handle the complexity of like telling the compiler, okay, they're going to submit a job, they're going to run it on this backend. They only have one object that they reason about, but the complexity is hidden in that backend implementation. There's no constraint in the backend. It's a Python class or be a Rust thing in the future, and it's all like dynamic, so you could implement that however you want. The other option is you could do it with multiple backends. And so you could say whatever that mesh system is provides a Qiskit backend to the application programmer, and it's just an object. They don't need to know what that object is. They just give it to the compiler and then submit to it. And so like you could do it either way. I don't think we're really thinking about expanding the data model to necessarily support that use case right now, because I think there's enough flexibility in it to express that kind of system if one was to exist. I think the closest analogy I can think of in my head is that Recon has developed an internal scheduler for, because they have 2 different quantum computers. They've got one from IBM and one from Quantinium, and they have this scheduler architecture that lets them dispatch to either one. And in my understanding, that scheduler gives the user a backend object based on what they request from the scheduler. And it's all tied into Fugaku.
We have a question from Smriti. Go ahead.
Hi, thank you for the amazing presentation. So I don't have a question specific for this, but I do have a question related to the estimator options and the quantum error mitigation techniques which are being offered through that. So I know that you can enable some of these options by setting them to true and also mentioning which amplifier we can choose. But is there like a modular way of accessing like the estimator particularly? Like I can get into the code and play around with the ZNE folding of the circuits or amplifier, yeah, or extrapolator, those kind of things.
Okay. So the way the estimator is defined in Qiskit, it carries some of the same mistakes that I described from back in V2, where it's like very freeform and it's hard to know what to deal with, like as a user or an application writer. So the estimator itself doesn't define those options. It's freeform. It's like, here's a freeform options object. Anyone that implements this interface can give you whatever options they want. And so like the IBM implementation of the estimator gives you all of these error mitigation options, and they're all kind of like opaque knobs, and they don't really, they might document it on the website what they say, but you don't get to see the code. And so I consider that a similar design mistake to the one we made in backend V2. What I was describing with the next version of the backend interface is something we're trying to fix with that. So in particular, so like you can turn those knobs and they give you that level of control, but the implementation is all done server side on IBM's implementation. There's the next iteration of the backend interface. We're looking at trying to change the execution model to describe that whole routine for estimation. So there's you might have seen on the IBM interface side in particular, there's this custom thing that's implemented only for IBM right now, which they call executor, which is like it defines the randomizations around doing error mitigation as a programming semantic. So you define your circuit in terms of the boxes, which you describe how you want to twirl your circuit, and it builds this sampling object that you can then use to identify the sampling or the randomizations on for the twirling for the error mitigation. And you can run that locally and get the same parameters and do everything locally, or you can submit it to the server and it just executes it in the same exact way that's done locally. And so those semantics are one of the things we're thinking about bringing into the next backend version, so that it's much more programmatic and descriptive of what's being executed for error mitigation, as opposed to just those knobs. I can say from like my internal knowledge of how ZNE works in particular, there's a repository, an open source repository that does ZNE with Qiskit. It's just using that. I don't know how the options you send on the wire for your request for the estimator translate to the options on that open source library, but the implementation, I believe, is the same.
Okay, got it. Yeah, I have been referencing that. So I guess I can wait for the next iteration of backend for this to take place.
Yeah.
Yeah. All right. Thank you
If
so
you are
much.
if you are running on IBM, you can use the executor, which is kind of like a prototype for what's becoming the next backend interface today.
Yeah.
But that's only for IBM, so it's not cross-platform because they just wrote that as a one-off for IBM.
Okay, perfect. Good to know. Thanks.
Any other questions? Okay, I have a few more. So you talked about target and describing the target. Is there any plans, and maybe you mentioned that a little bit and I could have missed it, but is there any plans to add specific capability discovery on the target so that the target can tell you what capabilities, hardware capabilities it has? Simple ones is like the number of qubits, but there could be other capabilities that are added in the future that can either the compiler can make use of or the application can make use of.
So, I mean, the target does describe all of that today. So like I didn't show the target API in particular, but like in the target right now, you can describe all of these capabilities of the hardware. That's like it's designed to describe for Qiskit's compiler, but also the user can query all of these things. Means that and query all of the capabilities of the particular QPU that you're going to execute on. And you can query that in code just as an end user. You can pull the target out of the back end and it's like, how many qubits do I have? Or if it's, if it has connectivity constraints, what's the connectivity graph? Give me an object of that so I can reason about it and work with it. So like a common use case that people have when writing applications is, especially on near-term hardware, you need to be aware of the connectivity constraints when you're building your circuit so that you don't try to, entangle too many qubits together and have kill your application with swap mapping. And so like you can just pull the connectivity graph off of there and build your application circuit referencing it. And so like it's a programmer interface, but it's also a tool for the compiler. And so I'd say that exists today. And like we classify the information with the same required optional custom. But this is also not fixed in time. We add to this. A very recent addition, for example, is angle bounce. So like in this, I don't think I show it anywhere. Well, I do in the AQT example. So here, this was a relatively recent addition. So AQT has this restriction on one of its gates can only operate. It takes an angle parameter, but the hardware only supports an angle between 0 and pi over 2. And so the target had no way of representing that. So they had a custom translation stage hook that would look at the circuit and translate all of the gates that were outside that angle set. And it's like, well, this is a common constraint. We should just add this to the target. So we added it to the target, and now you can express this constraint because it's a fairly common thing for people building quantum hardware that they can't tune up the gate with, an unlimited range of angle inputs. And so we extend this over time as new hardware comes out or expresses new constraints, and if you have a constraint you think belongs in the target, you can, work with the community, work with us in Qiskit to grow this, to cover additional constraints. I think one of the places as fault-tolerant hardware becomes real, we're going to improve this to be able to express the constraints for fault-tolerant hardware. Obviously, we'll have to.
Okay. Following up on that, when we talk about the compiler stuff, and you have this infrastructure for the compiler and the path manager, etc. Have you guys put any thought, because there's a lot of other people working with MLIR, say, for example, and also related to that is when you showed the if else and the conditional semantics, it was very specific to Qiskit, like there's a Qiskit object and some like dot if conditional or whatever. Have you guys thought about how you can incorporate that in that natural language construct, like if then else in C or whatever?
So I guess there's a couple of things there. So the first thing is like the reason we approached the compiler the way we did in Qiskit is that the quantum compilation constraints are very unique to quantum computing. And so leveraging existing compiler infrastructure didn't really buy us very much. And it's specifically like when you look at the classical side of the program, it's what you can do inside the quantum domain in like real time, and the coherence time of the circuit is very limited. So like if I go back to the slide with the control flow, this one, like the limitations, even on systems like trapped ions, which have much longer coherence time than like superconducting or some other modalities, there's still limits on what you're able to do in the classical side of the program. And so there's this notion of like you have a combined classical quantum program. In practice ends up being you have a mostly quantum subset of your program that might have a little bit of classical in it, but it's very limited. And then you have a classical program around it that executes that quantum kernel. And so building the dedicated infrastructure for doing the quantum compilation lets us be targeted in how we do that compilation, because that's what matters for the quantum computer, is doing that compilation well. And so like existing systems that like MLIR lets you define custom dialects, and you could put a quantum dialect in there, but then you'd have to write literally everything that Qiskit does in MLIR, which is not like designed for doing this. You totally can, and I know people are, but from our point of view, when we were building this infrastructure, first, I think MLIR was relatively new when we started this. At least it was new for me. But also, like when you look at what it provides, like none of the semantics are conducive for writing the kind of compiler passes we have in Qiskit. And so like you would be writing all of this in LLVM's toolkit. And so what it gives you is that flexibility to do the pass manager construction that I showed on a later slide. But that's not that hard. It's just an execution engine for executing a series of passes. And that's not that hard. So that didn't really seem that valuable to us for building the compiler infrastructure, so we could concentrate on doing the quantum bit well. And I will say with like the C API in particular, I think the people that are building MLIR engines, there might be some path here for like bridging the gap so you can leverage some of Qiskit's capabilities in your other compilation workflow if that's the path you want to pursue. One recent example I know of off the top of my head is TCAT has their own compiler framework. TCAT's a package built by Quantinium. They've started calling Qiskit transpiler passes internally when they're targeting superconducting devices.
And going back to that, using the language constructs, like if, like actual and if then else statement in C, and combine it with, like for example, here you have the with and you have the conditional for loop. Instead of writing it like that, can you write it, or are you guys thinking about enabling the or putting in the ability to say for, you know, ranged and whatever, like just using the normal syntax rather than the specific QC syntax like you have here?
So this was a debate when we added this to Qiskit, like a user interface debate. So for this, we settled on this. Like we looked at like you could, in theory, you could decorate a function in Python very easily, and then use normal Python syntax and just get the AST from the decorator and build out the internal objects the same way we do with this. Like this is actually a level of abstraction. We built this in Qiskit user interface to make it easier to use. You could also like write out what these objects are explicitly. They're all Python classes. You could do that by hand. We thought this was a better user interface because it was more indicative of like the actual context. Because if you do the other thing, like with the decorator and you read the Python code, it'd be very easy to confuse, oh, you're in a quantum function right now, but I also want like a classical if. It would be potentially confusing to do that. So we settled on this. It was a great debate at the time when we added this. I haven't thought too much about the specific syntax we're going to use for expressing this in C. To be honest, I've been mostly concentrating on the release that's has its first release candidate next week, and that figuring out the syntax was going to be a problem for the next release. I could see ties your hands a little bit. The things I'm thinking, it's like maybe we define a macro that like wraps a function or something. I'm not exactly sure. If you have any thoughts on like what you think would be more useful here, because like the thing I worry about is I worry about users mixing the context, and and so I'm just trying to think out loud here. Yeah, like I could see you have a macro that wraps that put in front of a function or something. Yeah, I'm not entirely sure what we're going to end up having it look like. If you have any thoughts on C though, like C++ or Rust or any more modern language gives you a lot of tools to do this, but C kind of ties your hands.
Yeah. No, we're not trying to solve the problem right now. I'm just like kind of thinking out loud or just trying to explore the roadmap that you guys have. And I have one last question. If we go back to the very last slide when you talked about the MPI and C++ code that Fugaku did, I was just trying to clarify here. The way it ran is you actually had multiple MPI processes using Qiskit C++ interface to generate circuits and submit those circuits independently to the backend.
So in this specific example, all of the Qiskit ran in a single MPI rank in rank 0 because it ended up being the the code that runs on the quantum computer, the quantum program, generates samples, which then feeds into a multi-node MPI process for processing the results. So there's a giant, this eigensolver in particular in this diagram, this SPD eigensolver, that's the thing that's multi-node using MPI. So it crosses multiple MPI ranks to do the linear algebra post-processing of the results. So all of this above this line all ran in a single MPI rank in a single process, because that's all that was needed for this application. That being said, nothing in the architecture like prevented you from having, multiple nodes in parallel submitting jobs to the quantum computer, except for that's, it's a serial resource. So like there's limited benefits to doing that besides building up a queue for its execution pipeline. But nothing here prevents you from doing that. It's just in this particular application, you get a stream of data out of the quantum computer and it's post-processed in parallel.
Got it. And sorry, one last question was so I was reading the latest paper out of IBM, the one that talks about HPC-QC, and I was wondering what is the relationship between Qiskit and QRMI. Is QRMI calling into Qiskit, or is Qiskit calling into the QRMI interface to do the run on the hardware?
So right now, QRMI mostly provides an interface to workflow schedulers like Slurm or any scheduler like that. So it provides basically a very unopinionated interface for some kind of scheduler to reason about quantum computers, and the specific implementation of what it sends from the user to the job on the scheduler, and from the job on the scheduler to the quantum system is completely open-ended, and it's not tied to Qiskit at all right now. I'd say one of the things I've been talking to the QRMI folks about is how to better integrate it with Qiskit, because a lot of the constructs in QRMI's abstraction is based on Qiskit, and there's like a one-to-one analogous with like what's in Qiskit's abstraction for a backend and what QRMI defines as an open-ended interface. And I think it would be very valuable if, like, when we're talking about having a new backend interface, how we can get QRMI to bridge that gap from the HPC scheduler to Qiskit more formally, because right now it's all ad hoc. So like QRMI defines vendor implementations for a specific vendor backend. So there's one for like IBM Cloud, there's one for IBM if you bought a dedicated system on premises using the direct access API. There's one for Pascal. And each of the payloads for that, for everything except job status, is right now open-ended. And it could be Qiskit or it could not be. I think all of the ones now, maybe not Pascal, but could use Qiskit. And so what I'm thinking is as that evolves, talk with them about like having the next backend interface define something that's conducive for QRMI to talk to, and get them to play together. But right now, they're mostly independent.
Yeah, it seems that there is an opportunity there because QRMI does this. So from what I understand, QRMI has like different types of APIs. You have the scheduler APIs that manages the resources, but you also have the runtime APIs, which, submit circuit, get back results, etc. Which I think that's what you're referencing. That looks, those APIs have a one-to-one correspondence with the backend. So there seems to be an opportunity to try to standardize this layer. And there's a lot of work being done in this with the QRMI and QDMI stuff, but there might be some thought about how to kind of align all these together.
Yeah.
Sorry, Oscar, go ahead.
Yeah, hi. I just wanted to kind of pick up on that. So I'm the STFC dev on the QRMI, and I don't think you're like a part of our formal kind of groups and things, Matthew. And if that is something that you're interested in, I think we'd really benefit from your experience. I know Otani-san is leading it from IBM side, but if you would like to be more involved and if you have ideas on how to make this better, I would be really, really interested.
Yeah, no, I think I've been talking to Otani internally at IBM about this, but I haven't started joining your community calls or anything. I probably should. I agree. So I'll reach out and look at joining those in the future.
Okay, awesome. I will also be delving into some more of the kind of Qiskit C API and running these workflows as I'm setting up a more kind of thorough tutorial at the moment. So it would be really interesting if you had any kind of takes on that as well.
Yeah, sounds good.
Okay.